Hi, everybody. We are very happy to have here with us Kelsey Lund. So Kelsey did her PhD at the North Carolina State University, and during her PhD, she also spent some time working in the Los Alamos National Lab, and she's currently a NEAS Yellow Fellow with at UC Berkeley. And she has for us a very romantic topic for today, for St. Valentine's. So she will talk about nucleosynthesis in neutron-star-merger remnant winds.
So thank you for the introduction and also for the invitation. I'm super excited to be here today and for the opportunity to share some of my work with you. So I'm actually going to start a little bit on theme. So today's Valentine's Day. That can mean more or less to you depending on if you celebrate or not. But if you were to go and use your search engine of choice to look up, the best gifts for Valentine's Day, what to get your partner for Valentine's Day. Usually there's some kind of mention of jewelry, usually some gold locket or a chain or a bracelet or, whatever. So there's this idea, of course, that things like gold, we see this in other fields as well, things like platinum, have some value to them. And then the question, of course, is what makes these things valuable? Are they inherently valuable? I think in the case of, you can pick your favorite airline or whatever, and there's usually some tiers of membership, and the top of the top is diamond. This is the best thing in the world. I don't think diamonds are that inherently valuable. They're pretty common. So I think that one we're not going to talk about. It's kind of marketing. But other things like gold and platinum actually do have some inherent value. And this has been persistent and pervasive throughout, cultures throughout most of our history, right? We have this idea that if you just keep trying and combining elements and you find the magical stone, you can make gold. But what makes these things kind of valuable a lot of times is their scarcity. So indeed, if we look at the distribution of elements that we have here on Earth, so I think this is a summary of the chemical composition of the Earth's crust. You can see that these things that we consider to be highly valuable are things like gold and platinum have extremely low abundances compared to everything else. And so this kind of goes into the question of well, why are some elements more rare or, and then therefore, more inherently valuable than some others? And this goes into the much bigger question of where do elements come from, and more specifically, how are they made? So this is, the value of things is kind of a nuclear physics question. And this is an extremely old question that we've been asking ourselves for millennia. It started with this idea of we took things, we took fire, we took elements, we stole them from gods. And then, over the decades, over the millennia, this kind of evolved into a more scientifically rigorous question into the mid 1800s when astronomers started to notice that the elements that were here on Earth were also in the stars. And so now this has evolved into the point where we have highly sophisticated technology, and we can take very detailed measurements of the different elements and their relative abundances in things like stars. So now we've gotten to the point where we have a pretty extensive listing and measurements of the different elemental abundances. So this is the solar abundance. And you can see everything from hydrogen and helium that would have been made in the very early universe, all the way out to very heavy elements like thorium and uranium. And I personally am very interested in the question of how heavy elements are made. So up until this iron peak, we can pretty much explain most of the elements through the lifetimes of stars, through different fusion processes. Once we get out past that iron peak, you start to need neutron capture processes. And then we can further divide those, and I'm going to explain a little bit in just a moment, into kind of two main different sources. And roughly each one is going to be responsible for about half of those elements beyond this iron peak. So what do I mean when I say heavy elements? I'm particularly very interested in the actinides. And I think that the actinides are really interesting because they are kind of a particular feature of the R process. So if we look at the chart of the nuclides, this is our nuclear physics periodic table that I'm sure you've all seen numerous times. I've sectioned out kind of the upper part of it, right? So you have the elements here on the vertical axis, and then the different isotopes of each element indicated by the neutron number along the horizontal axis. And I've colored them based on the decay lifetime of each isotope, right? So you can see the heaviest stable isotope is this lead-208 here in black. And then the lighter the color, the faster, the more quickly it decays. So the shorter lived this element is. So, okay, we have the heaviest isotope right up here, but then you can also see that beyond this, we have these extremely long-lived, although still unstable, isotopes, sometimes on the order of billions of years. So these are isotopes of thorium, of uranium. The problem is, if we want to make these isotopes, as I mentioned before, one of the kind of go-to ways for making these heavy elements is by capturing neutrons. Now, when you capture a neutron, you're more than likely going to be unstable to beta decay. So this process of turning that neutron back into a proton, thus moving you backwards, up and backwards along this chart of the nuclides. So you can see that you run into this issue where you have this kind of chasm of material that's itself is unstable on very short time scales, particularly to alpha decay. So that's just going to kind of lock you in the cycle of just putting material right back here in this lead region. And sorry, I'm indicating things with my mouse, but that might not be obvious. Sorry. So you can build material up to here, and then it's just going to kind of decay back. So a very simplistic way to get around this, very simplified way, is to just capture a bunch of neutrons on this, on this time scale, on a time scale that is shorter than the time scale of which beta decay is occurring. And then that's kind of the way that you can get around it, and you can make these very heavy, naturally occurring isotopes. So as I mentioned before, once we get out past this peak, this rapid neutron capture process is going to be responsible for roughly half of the material in the universe, heavier than iron. And so that's this solid blue line that I have here. And as I mentioned, actinides are, for the reason that I kind of described before, exclusively produced via the R process. So when we have one particularly interesting feature of some metal poor stars is that there are abundances, there are signatures of thorium and uranium that themselves are indicative of some kind of R process enrichment event. So then this leads to the question of, well, where do these R process elements get produced? So we know that neutron-star mergers are actually, I think at this point, it's fairly safe to say that they're not a leading candidate, that they're kind of confirmed. And, oh, geez, I'm sorry. I'm trying to, how do I go back to the mouse? Not that. Okay, now I can never get this to play automatically. But for a long time, we've had this idea that neutron-star mergers are a pretty good candidate site for production of the R process nucleosynthesis, right? Because you have this neutron-rich environment. And we had kind of visual confirmation of this with the merger event GW170817 back in 2017. And what kind of really supports this idea that we can produce at least out to the lanthanides in these types of events is you can see this initially very bright, but very rapidly decaying light curve. And I've highlighted exactly where this is in the optical image, but you can see this kind of much longer lived and much more slowly decaying red, much longer wavelength component to the light curve, if you will. And this is really supporting this idea that you have these extremely high opacity lanthanides that are produced in the ejecta of these neutron star mergers. Okay, so we've gotten to the point where we can say that at least half of the material past iron is made via the rapid neutron capture process. We know that neutron star mergers are one of the best candidates, and there's super strong evidence to support at least lanthanide production. But of course, in asking these questions, you open a whole Pandora's box of other questions, right? Because this is not a solved problem, right? So on the one hand, we need to know what the properties of these actually very neutron-rich nuclei that are involved in the R process, what their basic properties are. And there's a lot that we still don't know about the neutron star mergers themselves and the conditions that are found in these mergers. And then finally, overall, what actually can you get out of a single neutron star merger, and how does that play into the larger question of the history of the chemical enrichment of the galaxy? And then, of course, this is a kind of loop question that you use theory to interpret data, and then you use data to inform theory, and then you kind of go back and forth. Now, doing this is kind of complicated for a number of reasons, one of which is the different scales that are involved in these questions, right? So you have two neutron stars that themselves can live separately for a very, very, very long time. Once you start that inspiral event, it happens things start to evolve very, very quickly. So the actual merger takes, a fraction of a second. And so you're looking at very short time scales. I'll go back to the laser pointer here. You have extremely short time scales kind of in the merger itself, right? Then you get to the point where you're looking at different nuclear reactions. Now, I showed you on that figure with the chart of the nuclides that you can have decays that are happening on a fraction of a second, all the way up to orders of magnitude larger. And you're talking about, days, weeks, months, billions of years. Okay. And a kind of intermediate set, you have this idea of the kilonova. This is this electromagnetic signal that comes from the decay of these radioactive isotopes that you're producing. And this can take place over, hours to days to weeks. And then finally, you have this, this chemical enrichment that is the entire galactic history over, again, billions of years. So the way that I'm going to kind of frame this talk, this is, if you will, my outline, is by framing, talking about three different large questions, right? So one is this question of how off-stability nuclei affects nucleosynthesis, and specifically their properties and how we can vary the theoretical predictions of those properties. Then I'm going to talk about a project that I did that looked at magnetic field strength and the effect that it has on this post-merger disk. So after your neutron stars merge, there's this accretion disk black hole system that could make a very large contribution to the overall R process production. And then finally, I'm going to kind of very briefly talk about a recent project that what we did was we took kind of both of these two things together and used them to try and say something about the nuclear equation of state. And I'll have little checkpoints just in case there are clarifications that need to be made. So I'm going to start with the first one, which is this more nuclear physics question. And start by asking where sources of nuclear uncertainty come from. So this is this is a little video that I made that just shows some R process nucleosynthesis events. So this is going to build up this population that then decays, as I said, on very different time scales. The problem is, and what you can see is the different colors, is that this kind of gray area here is where we have data. It's where we have kind of experimental measurements of isotopes, masses, half-lives, etc. You could kind of see at the very beginning when I played it that just immediately the blue, which is the nuclei that are being populated, are outside of this range of data, right? So all of these different nuclei that are taking place or that are involved in the R process are largely unmeasured. So we don't know what their basic properties are. We don't know their half-lives. We don't know their branching ratios. And the nucleosynthetic outcome, what we predict, we can get from any one, single calculation depends a lot on these properties and the environment in which they occur, okay? So to start this, because we want to look at the nuclear physics and the properties of the nuclei, we're going to kind of parameterize, simplify the the environment part. Okay, so we need some time evolution. We need to know what the temperature and the density are. And so we have this parameterized wind where we assume this homologous expansion. So your temperature and your density are just decreasing with time. And we're going to set the initial composition with the electron fraction. So this is the neutron richness of the material. So the higher the YE, the less neutron rich. Okay, so we have these values of 0.21, 0.18, and 0.02. I've chosen these based on previous work. They're going to kind of highlight different physics, but I'm getting ahead of myself. So starting with the most kind of basic property of a nucleus is going to be its mass. And so there are lots of different models out there on the market. Different approaches in each case. We kind of take a large sample of them. Basically. And then in each case, we try to associate as best we can each model with its fission, associated fission barrier height models. And then in all cases, what we do in these calculations is we overwrite theoretical data with experimental data because we do have some measurements. So that's important to keep in mind. Now, I mentioned before that the rapid neutron capture process is kind of a balance between neutron captures and subsequent beta decays. Now, when you have isotopes that are unmeasured, what can happen is that whether you predict a beta decay or not changes not only that energy that you might get from a beta decay, but whether you're more or less likely to undergo some kind of other decay event like spontaneous fission or an alpha decay, and that can change the energetics. So in this case, for this work, what we did was we varied the beta decay rates using three kind of on the market global beta decay calculations. And you can just see here, these are color coded by the ratio of the rates to one of the older models, the Muller 2003. And then just generally more blue tends to indicate a slower rate overall. So you can see that globally, some models just overall predict slower rates than others, okay? And then finally, one last part of this, just I'm explaining the setup, is that we do an estimate of the light curve. This is just assuming that you have some shells of material that are expanding with different velocities. So concentric shells, each has a velocity and each has a certain mass that overall adds up to the ejected mass. And so we can kind of estimate, get an idea for what the bolometric light curve might be from nuclear heating from these nucleosynthesis calculations. So starting with the first case, what I'm showing here is the heating that's coming from beta decay as well as the overall heating from all reactions over time. So this is time in logarithmic days. And then this is the heating rate. So the dotted line is showing the total heating. And what you can see in the lowest neutron richness case, so the highest YE case, this was 0.21, the overall total heating is more or less well described by beta decay. It's making up most of the heating, especially on these kind of shorter day timescales. Okay, so we don't have a lot of, we don't have a lot of fissions, we don't have a lot of alpha decays. And most of all, what you can see by comparing the different bands of different colors is that there's not a huge variation from changing the beta decay rates, okay? What this means is that when we go through and we estimate our light curve, we don't see too much variation either. There's mostly overlap. The shapes are roughly similar. So it's more or less kind of all consistent, even though we're using 3 different sets of beta decay rates. When we lower the YE a little bit down to 0.18, what we find is that when we look at the total heating on a time scale of 1 to 10 days roughly, we can see that most of the heating is actually coming from alpha decay. And so that's setting that upper limit once we get to these later timescales and lower YE conditions. However, you can see that the overall shape is still roughly similar. We start to see a few differences, but we have a larger range of what we might expect the light curve to look like in that luminosity. Finally, if we lower it even more, what we see is that there's a huge variety. So the width of these bands is just growing significantly. Meaning that there's differences in the different mass models, what they're predicting. But not only that, but whether the spontaneous fission describes the upper limit of the total heating or not can also depend, okay? So once we have more fission in our heating, we get much more variation in our light curves. We can get brighter light curves and we can get differently shaped light curves. Okay, so then the question becomes, can we trace these to specific nuclei? Yes, but how? Okay, so what we can do is we can break up our heating calculation and we can go into what nuclei and look into what nuclei are actually contributing to the heating and where is their variation. So when we do this for alpha decay, what we can see is that differences in beta decay rates do have an effect on alpha decay heating, but for measured isotopes. So when you look at kind of the top heaters in your list of isotopes that are contributing to the heating, they're measured. They're these, 7 right here. But where we see the differences are in the feeders that eventually populate these measured isotopes. We can do the same thing for spontaneous fission. And here, I'm so sorry, I've been meaning to fix this, that you can see where there's data, where there's measurements, and kind of this light gray up here. So we have 3 isotopes that kind of consistently come out. So this is californium and I believe fermium, I think. Apologies if that's wrong. But then we have these isotopes up that are kind of very close to where there's data, but not quite. And what we're seeing here is really this difference that I told you about earlier, which is that differences in the beta decay rates can affect what the branching ratio is for that nucleus. And so therefore, given different models, we can make differences in predictions about whether there's going to be spontaneous fission or not. And again, this is changing the energetics of our light curve, of our heating description. Yeah, so one other result that I kind of do want to highlight a little bit in terms of just like which nuclei are, being populated and then decaying is a study that was led by Erica Holmbeck that I got to work on, which was looking specifically at the production of super heavy elements. So this is Z greater than 104. These are transactinide species. If these are made, what was found is that they can significantly impact the light curve. Okay, so we have 2 different cases here, which were selected kind of for, these are different mass models that are selected for and kind of to impair, if you will, suppress super heavy element production. And then if you compare the solid curve, this is, I'm sorry, let's start with comparing the solid colored curves. So this is the heating with all isotopes. This is just straight up, you take your nucleosynthesis calculation, you turn it into heating. If you then kind of post-processing remove all of the super heavy elements, you can see that that solid line changes to the dashed line, the colored line. And so what that indicates is that the presence of the super heavy elements is having an effect on these light curves. So that's pretty exciting. That could be significant. Okay, so I just want to do a checkpoint and you know, catch everybody up and make sure that we're all on the same page. Basically, that our process is going to involve a lot of unmeasured species, off stability nuclei. And overall, we find that when you take into account slower beta decay rates, you can get a difference. You can get a much brighter light curve on the timescale of a few days. Okay, so I'll move on to the second question, which is this question of the post-merger disk itself, okay, and how that evolves and how different things might impact it. So why the post-merger disk? If you look at this accretion disk, again, that I said forms after the neutron-star-merger, you can find kind of different components to it that lend themselves to our process production more or less effectively. So very, very broadly, if I color this by YE, this is just a snapshot from a simulation. You have regions that are extremely high YE in the context of neutron-star mergers, so 0.4-ish. This is very fast-moving material that's kind of entrained in this jet. You have this fast wind that's kind of intermediate values, but then you have this slow viscous material that can get actually to very, very low YE values. And so this is where you can get potentially get a lot of our process material. Why the magnetic field? What do we expect this? So again, these are also two different snapshots from two different simulations where all conditions are the same except for the initial magnetic field strength. And we parameterize this by this parameter beta plasma, which is the ratio of the gas pressure to the magnetic pressure. So larger beta plasma means weaker magnetic field strength. Okay, so we take 3 general relativistic neutrino magnetohydrodynamics disks with these different initial magnetic fields. Okay, what you can see is that at the same time, so this is about 4 milliseconds post-merger, these disks are at completely different stages in their evolution. Okay, and those differences in the time scale of the actual ejection of the material are going to have an effect on the conditions and therefore on the nucleosynthesis. At least that's the hypothesis. So just an overview of the code that we use. This is NuBlight. This is this GR new MHD, and the new meaning the Monte Carlo neutrino transport. So this is just showing how the MHD equations are solved for a full grid. This is a full 3D calculation. And then Monte Carlo methods are used to kind of do the neutrino physics. And then these are communicated back and forth. So the setup for this is that we run these simulations. As I mentioned, in all cases, the initial conditions are the same. We start with a roughly 2.5 solar mass black hole, YE of 0.1 in the disk, and then we have a disk mass of 0.12 solar masses. Then basically what we can do is we can track the evolution of this disk through tracers, and these are going to basically give us a recording of the changing thermodynamic trajectories, so the temperature and the density, as I mentioned before. And then we're going to run nucleosynthesis. We're going to do the nucleosynthesis calculation for all of those tracers. So this ends up being, roughly 500,000 nucleosynthesis calculations with PRISM. This is a code developed at Notre Dame and Los Alamos also. So great. So we're going to do all of this and see what comes out. So first, let's talk about the actual mass ejection. So what does the disk look like as material is being magnetically driven off of it? So what we find is that with a stronger magnetic field, so this is the leftmost case with the lower value of beta, what you can kind of see is as time goes on, as a function of angle above the midplane, so this is kind of the opposite of theta, if you will, you can see that we get a lot of early ejection of material. So this bright spot here indicates that there's more material there. As we decrease our magnetic field strength, the strength of that initial burst of outflow of material kind of goes down. And we can see that not only that the geometry of everything changes. So where on this y-axis, so where in theta space, this mass ejection is happening is also changing as a function of magnetic field strength. Okay, not only that, but if we take these, individual little histograms and we sum them up, we get that the total yields change as a function of magnetic field strength. So with the larger field strength, the stronger magnetic field, we get overall more ejecta, and that decreases as we decrease the field strength. So overall ejecta is increasing with increasing magnetic field strength, and the geometry where that different ejecta is coming from as a function of time also changes. So what that means is that we can trace this back again to we can make the connection between the nucleosynthesis conditions and the nucleosynthesis outcomes. So this is a kind of convoluted figure showing different tracers that are selected for having produced lanthanides in the top half of each figure and then actinides in the bottom half of each figure. Okay, and it's showing the electron fraction. So darker color purple means more neutron rich, so lower YE. And then I'm just comparing the cases with the strongest field on the top and then the weakest field on the bottom. And this is material that's kind of coming out the side. So this is that equatorial material, and you can see that it's making a lot of lanthanides, okay? And this is, again, indicated by this kind of dark blue. So where you have the darkest blue, that's where the lanthanide or actinide mass fraction is the largest. If we, instead of looking at the equatorial material, switch to the polar ejecta, we see that it's, as we kind of maybe expect from the figure that I showed you before colored by YE, we have much more neutron poor material. However, we're actually getting kind of high mass fractions for being so neutron poor. So we have YEs of almost, up to 0.25, which for the R process is pretty high. And yet we're not making a lot of actinides overall, but the tracers that are making them seem to be doing a pretty good job of that. And then we take all of the rest of the materials, so things that are not polar and not equatorial. And this is actually where we see a lot of variety between the two disks. So we have a variety of different conditions, and we have a variety of different nucleosynthetic outcomes. But a neutron-star merger is not a single tracer. It's the combined overall effect of hundreds of thousands of tracers. So we want to look at what the overall effect is on the nucleosynthesis. So what I'm showing in this figure is just the abundance pattern in terms of actual kind of unscaled, so just solar masses of each mass number. And what you can see immediately is the effect that I mentioned earlier, which is that a stronger initial magnetic field just produces overall more R process outflow. Okay, so it kind of looks, if you just glance at this, kind of unblur your vision or blur your vision, it kind of looks like the same pattern shifted up and down. And we'll see this a little bit when we actually scale the patterns and compare them to the solar. And if on a log scale, at least, the patterns look pretty similar, especially in the lanthanide region. This is pretty exciting. What we do get that kind of came out naturally that I'm very excited about is a variation in this, third peak, and especially in the actinides. So what we're able to do is, by simply changing the magnetic field in the disk, we're able to get a roughly consistent, robust lanthanide pattern, and then a pretty significant variation in the actinide production. Okay, so this is checkpoint number 2. I think I'm doing okay on time. Basically, what we found here was that using these super detailed post-merger disk simulations and by changing the magnetic field, we're able to predict differences in the geometric outflow of the material and also in the resulting nucleosynthetic predictions based on that change in outflow. Okay, so roughly our overall lanthanide production is changing by a factor of maybe 2 or so at most. And then our actinide production is much more sensitive to these differences in initial magnetic field strength, where we get a much wider variation. Okay, and then finally, this is supposed to happen automatically, but it doesn't. Okay, there we go. Now I'm going to get to the third part of my talk, which is where we're going to take kind of ideas from these two things, from these two projects, and put them together and try to say something about the equation of state. Okay, so I made some assumptions that I told you about earlier. When we set up the accretion disks for the GRMHD calculations, we assumed a disk mass of 0.12. And then when we computed the light curves way back, in the first part of the talk, we assumed an ejecta mass of 0.05 solar masses. That's okay. These are, these are motivated in part by simulation and also by interpretation of observation. You have to start with something, right? If we know where we make these assumptions, then we can know where we can change values and then use what happens when we change those values to kind of inform our interpretations, right? So this is that loop part of the problem that I mentioned at the beginning. Okay, so the basic idea is if you take two neutron stars, okay, you can't really throw them together without making a mess. Despite the fact that this is an extremely messy thing to do, we still try to do things like pick out individual components. So we have, that's why we talk about things like dynamical ejecta and secular ejecta and disk mass, disk winds and tidal tails. And we try to do our best to kind of characterize what's going on in this mess. Okay, this is all coming from extremely neutron-rich material. Neutron stars have extreme conditions from the perspective of nuclear physics. And so this is a wonderful laboratory, if you will, to probe the nuclear equation of state. Okay, and when we're talking about things like neutron stars, two key quantities for the equation of state are the TOV mass. So this is the maximum mass that a cold non-rotating neutron star can have, and the radius of a 1.4 solar mass neutron star. And these are usually, the equations of state are usually plotted on this mass radius curve, where for a given equation of state, this would be a single line on this curve. You can pick out if a neutron star has a given mass, what will its radius be? Okay, and what this equation of state is going to do is it's going to inform the distribution of material both during the merger while it's happening and after the merger. So where material is, whether it's unbound or not, by the time you finish the merger. Okay, so this is going to directly impact the remnant disk and the ejecta masses. And altogether, these are going to have an effect on the multi-messenger observations. Now, multi-messenger here means that we have the kilonova that I previously described, where it's this electromagnetic signal coming from radiation of our process, or the decay of our process nuclei. But we also have gravitational waves that can tell us about what the individual components of the binary were before they merged. And then all of that we can use to then go and inform what we predict about the nuclear equation of state. So let me actually take this diagram that I had before and write it out in terms of steps that we can follow, right? So we can use the equation of state to predict the disk mass. Then from that, some amount of that disk is going to become unbound in the form of ejecta. What is that quantity? And then from that, we can see if we can make an estimate of the peak luminosity and the time at which that peak luminosity occurs to kind of predict things about the kilonova. And then finally, put that together with gravitational wave information to say something about the equation of state. So this is overall the framework that I'm going to be following. So first of all, how does the equation of state predict what the disk mass will be, what the remnant disk mass will be? So this is the realm of numerical relativity, which is not my field. However, there's a lot of excellent literature on this, where lots of people have spent a lot of time running these simulations to see what happens in the merger. And so basically what you can do is you can relate the remnant properties to the equation of state properties, okay, via traditionally, I guess, one of three different quantities, the most basic being the compactness of the neutron star. So it's relating its mass to its radius. We also have this quantity, the threshold mass, above which you would get a direct collapse to a black hole. And then finally, we have the tidal deformability, which is just this how easily or not easily a neutron star is deformed when subjected to tidal forces. So then if you take lots of the simulations that exist in literature, is basically what I've done here in this figure, and just compared what the simulations predict for the remnant disk mass as a function of each of these three different quantities, then the goal is to kind of draw a line through these points, right? So find some functional form that relates the two quantities. And you can see that, different quantities may do a more or less good job of actually making that connection. So it might be easier to draw a line through these. So this is kind of what we did. Actually, before I move on to that, I'll just say that you might need, you're going to need more than one parameter to kind of fit through these. What we found was that the compactness of the lightest neutron star did a pretty good job, continued to do a pretty good job what we did in this work was we kind of updated a little bit. We took some of the newer simulations and basically reran some of the fits just to find a slightly different functional form than one that was presented in 2020. Yeah, just a slightly different fit. It has a pretty good functional form for this. So moving forward, this is the formula that I will use to relate the equation of state to the disk mass, or rather the binary to the resulting disk mass. Okay, so great. So then the next question becomes, how much mass becomes unbound? So I told you earlier that the question of how much ejecta comes from the disk, these simulations that we ran are quite expensive. Okay, so there's a lot of detailed physics in them. They take a long time to run. Our simulations that I showed you were run out to about 128 milliseconds post-merger. And if you have, for example, the case where you have a fairly weak initial magnetic field, that mass ejection can actually ramp up pretty late. So you can see that most of the material is actually coming out past the halfway point of the simulation. So 100 milliseconds, order 100 milliseconds, does not fully capture the evolution of the disk. And we found this from basically that same low magnetic field simulation was run out an order of magnitude longer to about 1.28 seconds, right? So actually an order of magnitude longer. And we did the same procedure. So this was a project led by Trevor Sprouse, where we looked at the tracers and the nucleosynthesis that came from that longer simulation. And what we found was that actually the material that comes out later is this, slow, viscous, very low YE material. And so if you kind of do a histogram showing the electron fraction from the short case, so the 128 milliseconds that I showed you before, this is the blue, and then you compare as the simulation moves on until the point that you get to the 1.2 seconds, your overall YE shifts significantly towards the lower values. And so what this means is that, okay, you're getting more lanthanides, more R process producing material, but overall you're also just getting more mass out. So that quantity that initially was in the lowest magnetic field case, about 2% of the disk, goes up to about 30%. Okay, 30% by the end of 1.2 simulation seconds, we were actually not convinced that the mass ejection had ceased. So indeed, even 1.2 seconds might not be sufficient to capture the entire evolution of the disk. I refer here to some other studies that found that about 40% might be that upper limit. So I think they ran out to something like 9 seconds and found that 40% was about as much as you're going to get. So what we're going to take at this step is that the unbound mass from the post-merger disk is going to be between 30 and 40% of that disk. So just keep that number in mind. Now the kilonova. So this is the part that depends a lot on the nucleosynthesis. Okay, so what we did in an old study that published back in 21 was that if you increase the wind mass, the effect that's going to have on your bolometric light curve is that it's going to increase the peak luminosity and it's going to delay it. So you can kind of see that here where each curve is a different ejecta mass. Now, if we just take that increase and that delay and we kind of plop it onto a figure compared to the different disk ejecta masses, you can see that there's kind of this, we can kind of form a curve, right? Now, if we change the nucleosynthesis, if we change the nuclear properties of the material, now here these are the green lines, now we have an entirely different set of predictions for what the peak luminosity is going to be and when that peak luminosity is going to occur. So now we're filling in our uncertainty space a little bit. Okay, so we can kind of fill in the region between that. And then we can say, well, we have observations, right? We have a kilonova. Can we pick out, if we divide it up into a blue component and a red component, can we pick out some peak luminosity and some peak timescale at which this occurs? And then draw a line through our newly populated uncertainty space. And so this is exactly what I've done. This is the shaded region here in both cases. And now if we just draw a horizontal line, essentially through where these shaded regions overlap, this is from this observation based on differences in nucleosynthetic properties, in nuclear properties we can basically say something about what the expected ejecta mass is from that observation. And then we can trace this back, say our 30 to 40% number, and get a disk mass out of that. So we're going backwards now. And so now that we have a disk mass, we're back at the beginning of our problem where we can say something about the equation of state, right? So we have, as I mentioned, we have our kind of constraint from our observations. We have our ejecta mass, therefore our disk mass. We have our formula that relates our disk mass to the lightest neutron star in the binary. And we have our constraint from gravitational waves. So this is a multi-messenger problem. And then finally, we have to give it some equation of state. So we take a very large sample of, I think, roughly 2,000 equations of state that are informed by chiral effective field theory. And we basically put them together and eliminated to some extent, constrained what the values of those equations of state might predict. Okay, so I'm just showing the most extreme cases here with the lowest end of this mass constraint and then the largest end of the mass constraint. And basically from this, we can read off what the 1.4 solar mass radius would be and what the TOV mass could be given these equations of state. And the cool thing from this is that, you know, our values are not super inconsistent with very large studies that are done using numerous sources of data from pulsars, et cetera. And just from this one data point, from this one kilonova, we're able to get fairly consistent numbers, but taking into account that there's a huge uncertainty in the properties of the nuclei that are forming the kilonova and the evolution, the post-merger disk evolution. So just something to keep in mind when doing these kinds of, you know, parameterized studies, if you will. Okay, so at that point, I think this is about the time that I will wrap up. And leave some of the conclusions here. Just say thank you all again for being here, and to my collaborators and, you know, different institutions. And at this point, I think I can take questions.